Welcome in the third part of the tutorial, in which we will introduce the meat and potatoes of the tutorial. That is to say, we will explain how to use events to store data and functions, to introduce a kind of object modeling. We will use Panola to specify music fragments, and we will start to build our framework of transformers that will be used in the final part to create the actual music. What is this idea of using events to store data and functions? Well, if you have some programming background, it's very similar to classes and objects in other languages. If you do not have this programming background, then brace yourself, because this may be a bit abstract for you. So what are these events? These were discussed at length in the project FreeJazz, the previous set of tutorials. So if you haven't seen those, by all means, first check those out. It will clarify a lot, I think. But events are, in essence, are they a collection of keys and values. So here I have a key data and I give it the value 1, 2, 3. Events are notated with round brackets. Now I can add stuff into this event using this index notation. So I add a key mysum, and I store for that key, I store a function. So again, functions are declared using curly brackets. And the function I'm storing into thing under the key mysum takes 3 arguments. An argument which I call self, an argument A, and an argument B. Now, what this self is will become clear in a moment, but the essence of the function is that it will return the sum of A and B. The last thing you put in a function is what is returned from the function as a result. With this function in place, we can now try to access the data in the function, which we do like we access also data in a list, but instead of using numbers to address, we use the keys to address the data members. So the key data, if you print the value of a thing of data, you would expect to see 1, 2, 3. If you call the function mysum with the dot value notation that we introduced in the previous part of the tutorial, then you can execute a function that is stored under mysum. And you see what I called self here, I pass into this function thing itself. And why do I do that? Well, like that I can use self to access every other key in thing during the execution of this function. So during execution of mysum, I get access to the value of, for example, data through the use of this self. And this works because the first argument I pass into the function is thing itself. So the event that contains all the keys and values. That's the part which may melt your brain if you haven't used object-oriented programming before. Of course, calling .value and then passing yourself into a function is not really the nicest notation. So again, supercollider here provides a shortcut syntax. And instead of calling this function by using this index notation, you can just call .mysum as if it were a real method on an object. And then you don't have to pass a thing as the first argument, but the language will do it automatically for you. But the effect is the same. So you will still execute mysum, and self will automatically get the value of complete thing, and A will be the first argument and B will be the second argument. Maybe we should try that out first so that we see what happens. So I'm going to execute this code block now by putting my cursor after the last round bracket, and you see that the complete code block highlights, and then I can press Ctrl Enter to execute it, or Command Enter on a Mac. And let's see what happened. So here we said thing of data, debug that to the post window, and it printed data is 1, 2, 3, which is exactly what we defined here, of course. Then, while executing mysum, we first printed self from the function. And if you do that, it here says printing self from the function. And as you can see, self contains the complete event with all the keys and values. and you can print self data using the index notation, or you can do it using the syntax shortcut notation, and both give you the same 1, 2, 3. And then the function returns the sum of a and b, which we here debug as sum3, or I haven't executed this yet, which we here debug as sum2, and that gives indeed 4 plus 5 gives 9. Now there's one very dangerous pitfall so events are not really meant to do this kind of thing. It's kind of abusing of the possibilities of the language, and there's a dangerous pitfall if you do that. And that is that so for events, some keys have a predefined meaning already. Like for example, events support a method called sum. And if we try to register our own version of sum, it will not work. So let me complete the code block here. I will now execute, and let's remove this because we already did it. Okay, so I will now try to execute thing.sum, and I would expect it to return a plus b, so 4 plus 5, 9. And I will post the result to the post window as sum3, and if I do that, I get something very weird. I get 12. 4 plus 5 is not 12 at all, so why did that happen? Well, apparently the event thing already has a key sum with a predefined meaning. And so when we try to register our own function into the event, it failed silently. Well, it didn't fail, but it will not execute. It will never execute this method with this notation. It will just execute the predefined method sum, which does something else, obviously, than what we expect it to do. Now, because this is very annoying, for example, another key that already exists is invert, and of course one of my transformations is also called invert. So when I try to make this code, I run into this problem, that it didn't work as expected. So there is a trick to avoid getting into trouble, and that is to use some extra code when you try to add methods to an event. This is pretty advanced, and I will not explain it in all of the details, but you can just copy paste it into your own code and use it if you like. So I'm adding to thing a new method, a new key save register, and I assign to it a function, and this function will basically check if something has been registered already under the name that I'm trying to register. So the save register takes 3 arguments: a name of a function, the body of a function, and then also some debug parameter, and it will check if under this name something has been registered already, and if so, it will throw an error at you. If not, it will register it just as if you would write it like this. So instead of now trying to add functions with the index notation like I did here, I will now call save register and the name of the function and then the body of the function. And this, if you use this way of working, you have the advantage that you will be warned by the system if you try to override something that has a predefined meaning. Like I said, this is pretty advanced, and it would be normal if you didn't understand every detail of this, but you can just use it as a trick. You can just copy paste it in your own code and use it for yourself. So let's try this. So I said before, sum should exist already in events, so this registration should fail because sum has a predefined meaning. Then when I add my own sum, that should not fail. Because that has no predefined meaning. But then if I try to register it a second time, it should fail again because it already has a predefined meaning because we registered something with already. To see that the last time fails, I will make this a multiplication. Let's try to execute this code. So it should first try to register a sum function. That should fail. It then tries to register on my own sum function. That should not fail. And then it tries to register my own sum again, which then again should fail. And then I still expect that this one that succeeded and that does an addition will return 9 as a result. And exactly as we expected, for the first one it throws an error, cannot registering sum would overwrite a member that exists already. And for the second registration of my own sum, you get an error, cannot register my own sum twice. And then it has executed not the multiplication but the addition. So it's really this one that succeeded and not this one that succeeded in registry. So this is a way to add functions, store functions into an event without having accidents along the way. And I will be using this way of registering functions into events later in the tutorial. So that's why I wanted to explain this. Even if you do not understand all the details, you can just copy paste this piece of code into your own code and use it, like here. That's what I wanted to say about using events for storing functions. Why would you like to store functions in events? Well, they keep everything quite tidy and nice together, and it keeps your code very readable, which is maybe not important while you work on it, but if you revisit your code in 1 year, you will be glad you paid some attention to readability. Then we come to specifying music fragments, because we will be calculating variations on a theme. That means we need to have a way to specify our initial theme. And what I see many people do to specify music fragments is to make these p-binds, which were explained at length in the previous tutorial on Project FreeJazz, so be sure to check that out if you haven't seen it. And they will make these long lists of numbers with notes, with durations, and then again with amplitudes and other keys, which is fine if that works for you. By all means work like that, but it's a nightmare for maintenance. Suppose I want to change this note from a quarter note into 2 eighth notes. Here I can change 43 into 43,43. That's no problem, of course. But then the misery is I have to find the corresponding numbers in all the other lists for durations, for amplitude, for legato, for everything you've specified in the p-bind, so that I can also update those numbers. And that's the hard part. So people will often organize their code measure by measure, so that they have some way of navigating between all the numbers. But it's very annoying to work like that. At least, first of all, I cannot reason in MIDI numbers. It's very unnatural for me. And second of all, this maintenance of trying to update your score, it's a nightmare, a complete nightmare. For that reason, I came up with a different way of specifying patterns, and I created a quark called Panola, which is short for Pattern Notation Language. And Panola allows you to specify musical fragments using a kind of text-based music notation. So for example, here we have an A note in the 4th octave, and it lasts it's a quarter note. And then we have an A, there's no octave specified, which means that it uses the same octave as before, but it's an 8th note. And then we have an E in the 5th octave, which is also an 8th note, and so on and so on. Then you also see here there's a round bracket, and a round bracket times 2, so this allows you to specify repetition. It's a very concise notation. This is the complete right-hand side for our theme that we will use as a starting point, and this is the equivalent of this in traditional way of working would be all these lists of numbers, which are in these numbers I cannot see what is being played at all. In this I can even sing it if needed on site. It's a much easier way of specifying music fragments. But of course, you now have this Panola with some long multi-line string. That doesn't look very handy for calculations. It's just a string, and then we need to parse it into some numbers, because otherwise we cannot do any calculations. How do we do that? Well, luckily, Panola, of course, is not just a string-based thing. It has provisions to extract from these strings all the properties you need to create your p-bind. So it can, for example, turn the string into a MIDI note pattern, and the pattern you can turn into a stream, which was explained at length in the Project Free Jazz tutorial, so please, if you haven't seen those, check them out first. And once you have a stream, you can get all the values from it, and then we can debug all these values to the post window. And same for durations. From the same Panola string, you can also extract the durations as a pattern, turn those into a stream, and then turn them into numbers. So let's try this out for the right-hand side. So RHS stands for right-hand side, and LHS stands for left-hand side. So this is the bass, more or less, and this is the melody. So let's try it out. We will take these Panola specifications and turn them into the MIDI numbers and durations. And this is exactly what we see here. These are the numbers, and these are the durations, and these are very handy when we try to make calculations, when we try to calculate variations. That's all I'm going to explain about Panola in this tutorial. Maybe I will do a separate tutorial on all of Panola, because it's a lot more extensive than what you see here. But this is enough for what we need today. And then we come to the biggest part of this part of the tutorial, and that's our framework of transformers. So transformers, as I define them here, are functions that take a list of notes and durations and transform them into a new list of notes and durations. So if you remember from the first video in this series, we had this retrograde, which reverses lists and notes and durations, and we had all kinds of transformations. These are the ones that we are going to make now. As before, I'm using my safe registration code to avoid overwriting existing keys by accident, which would not work anyway, or not at least not work the way we would like it to work. And the very simplest transformer we can think of is one that does nothing. This is just for demonstration purposes, of course, because I want to explain something about how to make the interface for these transformers. One of the requirements I kept in mind while making this is that every transformer should be able to be combined with every other transformer, so that we can compose different transformers together to get very complex results. And that means, to make that easy, you should pay attention to the following. The input format of your data should be the same as the output format of your data, so that you can just chain together different calls to the transformers. And because we want to return a list of notes and durations, and notes are themselves also a list, and durations are themselves also a list, so we really have a list of two lists, where here are the notes and here are the durations. Because that's the only way to return multiple values from a function, is to return them in a list or in an event, but I chose a list here. That means that also in the input I will expect that same list of lists with notes and durations. And that will make it very easy to compose together multiple transformers when we start to actually create our music. So here I implement the retrograde transformation. If you remember, retrograde will reverse only the notes and not the durations. So if you think about it, we have here a list of notes and a list of durations. That's the shape, if you like, of this argument note, DURS, notes and durations. So that means that the zeroth element of this big list is this. That's the zeroth element. Those are just the note numbers. And the first element in this list, notes, DURS, is all the duration values. So when we try to retrograde only the notes and not the durations, we take notes durs 0 and we reverse those. And we just keep notes durs 1 and keep those unchanged. We put all of that into a list and we return it from the retrograde transformer. Okay, I hope this is clear. It's quite crucial to understand what happens here, because that's the basic way that all the rest will also work. So if you remember from the first video, retrograde all will reverse both the note values and the durations. So here we return a new list that contains the notes in reverse and the durations in reverse. Then we have we add a method inv. So at first I had used invert here, but apparently that's a predefined key and it got me into a lot of trouble. If I would try that now with the save registration that I explained before, we would not get into that trouble, or at least we would get an error message, so it would fail to register a function with the wrong name. So what will that do? Invert inverts music around the pitch. So we need two arguments now. First is the list of notes and durations. And we also need to pass a pitch, a note number around which we will invert. And the mathematical formula for inversion is this. You can check it on a piece of paper if you like, or you can just believe me. And now we can already use the power of our transformers. I have here a transformation called invert and retrograde. And we will compose two of our previously defined transformers together. So we will call retrograde on the result of invert. And this is possible, this composition is possible because the input arguments and the output arguments are always in the same shape. So we don't have to worry about transforming the outcome of one function into a format suitable to pass into the next function. They are made such that they are compatible by design. You can already see that you can combine many of these together and get complex results, but we will make some crazier stuff. Until now, we never introduced any new notes or any new or extra notes or extra durations. We always kept the existing notes, we just reversed them in time, but we never introduced any new notes. And that's changing with the next set of transformations that I'm introducing here. One is called ARP, which could refer to some kind of arpeggiation. And here we will first get the notes from our input argument and the durations from our input argument. And now we will calculate new notes and new durations. And how? We will go over the given notes 2 by 2, so with the do adjacent pairs that we explained in the previous part of the tutorial. And then for a number of octaves that we specify as part of the arguments, but with a default of 0 and 1, we will take the adjacent notes in the list and we will add the octave to it. So if you, for example, you have notes A and C, you would get here an A in octave 0, C in octave 0, and then an A in octave 1 and an A in octave 1. So you transform two adjacent notes into a kind of arpeggiation. But when we introduce extra notes, I do not want to change the complete duration of the fragment. So I have to also introduce new durations, and these durations have to be shorter, of course, so that the total time duration of the fragment doesn't change. And that's important because we will play our melody against some bass line, and of course the two have to keep in sync at all times, at least in this music. So that's for this arpeggiation transformation. Feel free to edit the code and then put in debug statements and try to figure out exactly how everything works. And that's the purpose, that you also try to experiment with the code and try to find out exactly what happens. So then there's the spray transformation, which we also explained in the very first video. where we replace notes with a very short spray of notes, more or less. And the code for that is here. So again, we introduce extra notes, and the number of extra notes, the density of the spray, if you like, I determine here randomly. So I choose between 7 and 1 notes. That means that every time you play the piece, you will get a slightly different result. I like to add some randomness in my scores, and this is one such place where you have randomness. So every time you play it, it will give a different result. And as before, if I add extra notes, I also have to add extra durations, and I make sure that the total duration of the fragment does not change compared to the original duration, so that it remains in sync with my baseline. And then as a last transformation, I have the interpolate transformation, which again uses the do adjacent pairs, and then it will interpolate new notes in between the old one, the two adjacent notes in the list. Finally, I have some utilities. Utility note will convert a note name into a MIDI note number, and I'm doing that by leveraging the power of Panola again. This function I will use when specifying inversions, because if you remember, inversions do not only take notes and durations, but also they take a pitch around which you want to invert. And then I have a function called asPattern. That's a function that takes a list of note and durations, and then also some other parameters, and turns that list of notes and durations into a fully fledged pattern, which you can either play to an external synthesizer or to the internal synthesizer of supercollider. That concludes this part of the tutorial. If you have questions about stuff that is not clear, let me know in the comments, and see you in the last part of the tutorial, where we will start to use these transformations to create music.